to leave the room at 1:20 sharp because there is a CFA-wide meeting later. So I would appreciate if speakers can. Okay.
It's gone. We're already having troubles.
Yeah.
Haven't even started yet, and already in big trouble here.
Yes.
No, so we stay there forever. Stop share. Yep. Okay, now I got it.
Okay, and then sharing before sharing.
Oh, we stopped sharing.
Yeah, it was
wow.
To reshare. Yeah.
It's gone.
Yeah. Okay. Sorry for the short interruption. So the first speaker of today is a local one, Bogdan. Let me go over briefly in his introduction. So got his PhD at Max Planck Institute for Astrophysics in Munich, in Germany. Then he joined the CFA as an Einstein postdoctoral fellow. And after that, he joined the Chandra-JWST Center, where he was, and I think he still is, part of the calibration group. He works on a wide range of science topics over the years. These include the studies of the circumgalactic medium in X-rays, then exploring the WIM, which I think is a wormhole intergalactic medium in absorption, studying correlation between supermassive black holes and their host galaxies and clusters, and searching also for supermassive black holes in the highest redshift galaxies. You might know also that he's currently heavily involved in the development of the LEM Emission concept, where he's also leads of the science team and co-chair of one of the teams, and is also co-chair of the circumgalactic medium science working group. Okay, he's talking today to us about detecting the first supermassive black holes, the Chandra-JWST synergy. And the floor is yours.
Yeah, thank you. So there will be no LEM discussion today, no CGM, only high redshift galaxies and high redshift AGN. Some people are very happy about that. Okay, so I'm going to tell you about this unique synergy that we have started between Chandra and JWST, and the goal of this work is to find supermassive black holes in the early universe in some of the highest redshift galaxies. So I'm not only going to talk about one paper which came out, I think last week. Was it last week? Yes, last week in Nature Astronomy. But there is also another paper which will be submitted in the next few days, and hopefully will be on archive like next week, about another supermassive black hole candidate in a very, very distant galaxy. Okay, so I had fabulous collaborators, co-authors fabulous co-authors on both of these papers, and some of them are here. So thank you very much for all your hard work. So why do we care? Well, because of course we don't only care about high redshift galaxies and high redshift AGN supermassive black holes because it's cool to have something so distant and so early in the universe, but we of course also want to do some science with it, and we want to understand how supermassive black holes form. In the very traditional picture, and I'm not going to spend too much time here, in the very traditional picture we have two different and potential formation channels on describing how black holes form. One of them is the so-called light seed scenario, and the other one is the heavy seed scenario. Looking for the stick, which is so one of them is the no, that's fine. Oh, okay. Don't worry, guys. Light seed scenario and the heavy seed scenario. So in the light seed scenario, supermassive black holes originate, or they are seeded from the collapse of population-free stars, and typical seed masses, according to theories, is between 10 to 100 solar masses in the light seed scenario, right? So they start early on, somewhere here, but with very low masses. So they have to do a lot of work, for example, to get to the observed quasars, which are at redshift 6, so roughly 1 billion years after the Big Bang. They have to, accrete very heavily, and oftentimes they have to accrete at super Eddington, or maybe even continuously they have to accrete at super Eddington, which is very difficult. Now, the heavy seed scenario alleviates this problem because black holes form from the collapse of massive gas clouds in this scenario, and they are seeded with really, really big masses, 10 to the 4, 10 to the 5 solar masses. So in this case, episodic accretion, so if you start from here, direct collapse black hole, then the episodic accretion or accretion at the Eddington rate might be just fine to reach the observed quasars at redshift 6. But what we really want to do is we want to test the co-accretion higher redshift, because many models, if you look at models, the real information about the initial seeding is hidden at really high redshift, so at redshifts higher than 7. So this is a theoretical prediction between the heavy seed and the light seed models, and it shows the predicted accretion density of black holes in these different scenarios. And the key message here is that the difference really starts to appear at redshifts higher than 6, 7. So, and ideally, this is where we have room for supermassive black holes. So this is what we are trying to do. Now, let me tell you about this specific program that we started, the Chandra-JWST observations. So of Abell 2744. So Abell 2744 is a very famous galaxy cluster. It's one of the Hubble Frontier Field clusters. It's, as you can see, on this beautiful image done by our EPO, Chandra EPO office. So the purple shows the X-ray emission. The beautiful underlying image is the JWST image of this galaxy cluster. So this is a massive merging cluster. Even though I like galaxy clusters, I like galaxy cluster physics, I'm not going to tell you anything about this today, okay? So we keep sticking to high redshift black holes. So this is also a gravitational lens. And it's a gravitational lens, which is great, because it magnifies the faint light from galaxies. And what's even more important, it magnifies the faint light from the supermassive black holes sitting in these very, very distant galaxies. Because it's such a wonderful target, and it has the potential to uncover high redshift galaxies, and it has a potential to uncover high redshift supermassive black holes sitting in these galaxies. It was the target of multiple early JWST programs, for example, for the GLASS, or the Uncover program itself. And accordingly, James Webb revealed a fairly large population of high redshift galaxies. And when I quote a fairly large population, then I should say 19 galaxies which are at redshift 9 or higher redshifts. We followed up the essentially these JWST observations with Chandra. The total exposure time is 2.2 megaseconds. And what I'm going to tell you about are 2 redshift 9 galaxies with X-ray AGN, which hosts supermassive black holes. One of them is a really nice detection, and the also very nice detection has some caveats though. So I'm going to refer to it as a candidate. Now, this is a beautiful image. I did make this image. Peter Edmonds and his team, so the Chandra EPO office did this beautiful image. And I'm very proud because this was the astronomy picture of the day, I think sometime last week. So this is the JWST image. Here is the galaxy UAZ1, which I'm going to tell you first. And this is a smooth Chandra image of the supermassive black hole sitting in this galaxy. Of course, this is much more extended, and the reason why it's much more extended is because Chandra pixels are much bigger than the JWST pixels, even though Chandra has an excellent angular resolution. So let me tell you a few words about UAZ1. UAZ1 is sitting at redshift 10.1, quite precisely 10.07, and this is a spectroscopically confirmed galaxy. So initially we only had like photometric redshift, but now we have also spectroscopic redshift, which tells us exactly that this galaxy is redshift. And you can just tell that it's a real alignment break dropout galaxy, is that it's all the images that are showing UAZ1 shows up in all the JWST bands, except for this one, which already tells you that this galaxy is probably at redshift 10, and indeed spectroscopy confirmed that. It also has a pretty good lensing magnification. Lensing is roughly factor 4, and star formation rate is roughly a solar mass per year, and the galaxy is very tiny, roughly 10 to the 8 solar masses. So it's quite amazing. We see a 10 to the 8 solar mass galaxy at redshift 10, 470 million years after the Big Bang. Quite impressive. Now, only thing you have to do is to look at the Chandra image of this very same galaxy. This is the Chandra image, by the way. This is again a Chandra image of the galaxy cluster. Here is UAZ1, and then this is the Chandra image zoomed in. So you see here a couple of pixels, and you see here the contours from JWST. So these were the galaxies. It's right exactly where these bright pixels are. So we can calculate how many counts we have in the source region. We can use this region, this bigger annulus, as the background region. And what you will find is roughly we have 42 counts. Half of them are roughly background, and the other half is source. You do the math, and then what you find is that we detect the source with roughly 4.2 sigma significance. That's 4.2 sigma detection level. We can also further verify this detection threshold, this detection level. What we can do, we can take a big region around this source, a little bit bigger than this one. So we can take a bigger region, as I said, and then we can exclude the UHZ1 regions, the galaxy region, and we can assume that we can ask the question, if every single pixel has a point source, and we extract the source region around every pixel, then how many counts do we get in each of those little regions? Now what we get is like we have a bunch of source regions, and we can count the number of counts in each of these regions. And what we find is that essentially we have this distribution, we get this distribution of counts in every one of those, not regions, but the source regions. And what we get is that the average number of counts is roughly 20. The peak of the distribution is at 20 counts. The mean background that we subtracted using this annulus was roughly 21 counts. So this analysis assumes or comes to the conclusion that the source is detected with a 4.4 sigma detection threshold. So both of these values are consistent. Now, of course, the issue that this is sitting very close to the cluster center, right? So what you need to do is we need to make sure that it's not coming from the cluster. So in order to do that, we made a very simple spectrum, it's a simple spectrum because it's based on roughly 40 counts here. And of course, we try to fit it, because why not? And the fact that the source is only detected in the hard band, roughly in the 2 to 7 keV band, but it's not detected below. And again, remember that it's redshift 10. So what we are talking here is roughly 20 to 70 keV. So we became a hard X-ray instrument. We became, it's not Chandra anymore, it's Mustar at this point probably. And because of the fact that we don't detect in the 5 to 50, roughly 5 to 15 keV band, it implies that this is very heavily absorbed. Okay, so the obscuration level is high. And what we can also find out from the spectrum is that the spectral shape within this source region is very different, or the spectral characteristics of the photons are very different than that of the cluster, right? So here we have a typical cluster-like emission with a roughly 10 keV temperature. And here we completely lack this component. So we can see, so we have a very different spectral model essentially. And the conclusion is that this has nothing to do with the cluster because it's so much harder. We can compute the bolometric X-ray luminosity. So we can compute the X-ray luminosity, and then we can compute the bolometric X-ray luminosity. I'm going to skip a few steps because we have to finish on time. And what we get is that the X-ray luminosity, the bolometric X-ray luminosity of the source is roughly 5 times 10 to the 45 ergs per second. This being X-ray is the best we can assume that this is assuming that the source is assuming an Eddington. So we have a black hole mass of roughly 4 times 10 to the 7 solar masses. If you might remember, the stellar mass of the galaxy, it was 1.5 times 10 to the 8 solar masses. So you divide the two numbers, and what you get is that the black hole mass to stellar mass ratio is roughly 0.3. Now, this is quite amazing because in nearby galaxies in the local universe, this ratio is much, much smaller. It's around 0.1 to 0.2%. Okay, so here it's like 100 times larger, a few hundred times larger, which is pretty amazing. So let me tell you real quick about the other source. This other source is again 8x2744. So this other source is not really at the center anymore. It is really in the outskirts of the galaxy cluster 8x2744. And you can see here the source GHZ9 at redshift 10.4. Also a dropout source, but unfortunately in this case we have to we have to be happy with the photometric redshift. And again, this is like this is a dropout source. You see in the short wavelength, you don't see it anymore. The redshift, we place the redshift of this source at roughly 10-ish, 10.4, but note that unfortunately we have a lower peak at redshift 2, so there's a small secondary peak. Star formation rate and stellar mass are roughly similar, so several times 10 to the 7 or 10 to the 8 solar masses in this case. Let me jump right to the case. So this source is detected in the 0.5 to 3 keV band, okay? And let me tell you the statistics here. So in a source region, we get like 26 counts roughly in a 2 arc-second source region around the source, and unfortunately the PSF is pretty broad here. But here is the source, okay? Here is the source, it is a JWST Chandra overlay, and I will tell you in a second about some difficulties. You can account for background using different ways, but what you get is that the source is detected roughly at 4.3 to 5.4 sigma significance level. Since this is not obscured, we can we don't need to do very fancy spectral analysis, so we can straight away compute the X-ray luminosity, the softband X-ray luminosity, and then we can compute the bolometric luminosity of this source. And then, as before, we can compute the black hole mass. What we get is roughly that the black hole mass of this galaxy is 8 times 10 to the 7 solar masses. So, and the black hole to stellar mass ratio is even higher, it's actually 1.6, so it seems pretty interesting, I would say. Now, as I said, this is a black hole candidate. So there are a couple of issues and a couple of complications with the analysis. One of them is this thing here. This is a Milky Way star, roughly 4 arc-seconds away from G8Z9. It is not really a problem. This is JWST image. It is not really a problem for JWST because JWST has this fabulous 0.05 arc-second pixels, and it's just fine. However, once you move to Chandra, you start to have issues. So this is the Chandra image, this is the star, and this is where the galaxy is. So the issue here is that the source is located at 6 arc-minute from the Chandra aim point, which means the PSF is pretty broad, unfortunately. So some of the counts coming from the star will spill over into the source region. So we can try to account for that. We can model the PSF. We can measure hardness ratios. So what we find is that this source is not, so the source is really not dominated by the counts from the star. You can also look at this wedge region here and look at, look how many counts we have here versus here. And you find that this source is really at 4.5, 5 sigma on top of any of the local backgrounds and any counts that would come from this star. So there is really something excess. Now, the other issue is that we have this other galaxy right here. This is a lower redshift galaxy. This galaxy is roughly is at a redshift of roughly 1 or 1.5 or something like that. And unfortunately, this galaxy is located about 1 arc-second away. So this is G8Z9. This is the redshift 10 galaxy. And this galaxy is located roughly here. There are no Chandra pixels here, sorry, no Chandra counts at the position of this lower redshift galaxy. But, and actually the center of this galaxy from the center of the X-ray source is roughly 1 arc-second. So, however, we are, again, I remind you that we are 6 arc-minutes away from the Chandra aim point. So there might be things happening here. What we know is that the Chandra-JWST astrometry is accurate roughly within 0.3 arc-seconds. However, there might be systematic positional uncertainties up to 1 arc-second between at such large offsets, such large off-axis radii, so 6 arc-minutes, and for faint sources, especially because it might be more difficult to determine the centroid. So this is the main reason why I refer to this particular source as a black hole candidate in this redshift 10 galaxy. It's because the reason that we have this nearby lower redshift galaxy here. Okay, so again, the most likely association is with G8Z9, but we cannot exclude this super high confidence that this lower redshift galaxy has nothing to do with this source. So, but for the time being, let's assume that we have a black hole, UHZ1, or a black hole in UHZ1, and we have a very nice black hole candidate in G8Z9. So this black hole candidate can be confirmed by follow-up JWST observations. Now let us consider how these black holes might have formed. And in order to do that, let's just draw a growth curve of the black hole seed. So let's assume that the black holes start to grow at redshift 25. And then what we want to understand is how could they grow to redshift 10. So from here, from redshift 25 to redshift 10, I think this is like a 200 million year or period, 300, somebody can check, 300 million year period. If you assume Eddington accretion from the light seed with 10 to 100 solar masses, then from redshift 25 to redshift 10, you can go to roughly 10 to the 4, 10 to the 5 solar masses. The black hole mass, the inferred black hole masses of these galaxies were up here between 10 to the 7 and 10 to the 8 solar masses. So they are like 2-3 orders of magnitude below what you would expect or realistically expect. If you do the same thing with the heavy seed model, then you can easily grow Eddington accretion. However, in order to do to make the light seed scenario work, you need to do 2 times Eddington accretion. And my theorist friend can tell you that this is virtually very difficult or even impossible, some would say. So essentially heavy seed, so these growth curves, simple considerations and growth curves very strongly favor the heavy seed model. So let me show you one more plot. This is where these are local galaxies. So the black hole mass and large mass relation for local galaxies. So UHZ1 and G8Z9 would be here. So roughly 100 times bigger black holes relative to the stellar mass of so the black hole to galaxy stellar mass ratio is 10 to 100 times larger than for galaxies in the local universe. And let me tell you, this is my last slide. This is my last slide, okay? I see the chair is approaching me. So let me show you this very last slide again. And what you can do if you already have 2 sources, so one with nice black hole and one candidate, then you can already do a luminosity function, right? I don't get why people are laughing at this. I'm that serious here. So this is a luminosity function of sources at redshift 10, and this is luminosity function of sources at redshift 8. Okay, and these are this is more than 2 sources. Okay, so this is like, I don't know, maybe 10 sources. And the dashed lines are the heavy seed and light seed theoretical predictions. So we can now compare the luminosity, the observed and theoretical luminosity functions, and we can also reveal the black hole seeding mechanism. So when we write a proposal, then we say kind of things like this. We are going to reveal how black holes are seeded because we are going to compare observed and theoretical luminosity functions. So here we do it. And what you see is that in case of the redshift 8 sources, the observations are a little bit above the theory. But what's important is that at redshift 8, they are almost the same. The heavy seed and light seed models are almost the same. So you cannot differentiate them. If, however, you go to redshift 10, they become different. But now what we see is that our luminous or data point based on 2 sources, okay, 2 sources, so it's really a lower limit, is like way out of the realm of theory. So it's so much higher, right? So it should be here. So it's orders of magnitude higher. So what does it mean? It probably means that there are multiple scenarios that can result in heavy seeds, and current theories are seriously underestimating the efficiency of producing supermassive black holes in the heavy seed scenario. So indeed, if you want to look at the paper, you can scan. That's it. Thank you very much.
Okay, wonderful thing. Wonderful job. So, do any questions from here?
Very nice. If is it okay? If it's not that if it's not associated with the high redshift source, high redshift galaxy, and if it's associated with the lower redshift one, what would be the luminosity of on the source?
I don't remember that I calculated once the black hole mass, so it would be something like 10 to the 6-ish. So it would be, the black hole mass, galaxy mass would be still pretty high. So even at redshift 1.5, it would be still a pretty surprising and interesting source, but probably not as interesting as redshift 10.
Okay, last question.
Nice talk. I don't know if this is actually working. The two brief questions, hopefully. One was, where would, in that last plot you showed on the final slide, where would GNZ11, what would that do to that data?
Yeah, I can't go back anymore. I don't know. So GNZ11, that's another field. So I don't know how it would modify, because that particular field, so you need the area that you surveyed and you need the number of black holes. So I'm not quite sure. But in general, it seems that every one of these James Webb pointings seems to have a very high redshift AGN, depending on which one you believe that was published or which one is you don't believe. But I think, if you add the corresponding JW area, and it would probably be at the same position, more or less.
The brief for the follow-up is it still obscure? Is the versus source too obscure for JWST follow-up to detect it in?
Yeah, so that's a very good question. So we have the near-spec follow-up. So after we knew that Chandra sees the source, and we don't see it with near-spec, which is perfectly fine, and expected it. I mean, we expected that given how obscure that source is. So in the near-spec spectrum shows the characteristics of a typical galaxy, which has a little bit of star form, well, quite some star formation relative to stellar mass, but we didn't expect to see it with near-spec. The main goal of that near-spec observation was to get the redshift of the galaxy, which we did.
Thank you. Let's thank Eko Shigri.
I don't know how to.
We know where is the other person.
Yeah, I know, but I have to stop.
Yeah. Okay, thanks. Let's move to the second speaker. So, okay. So the second speaker is Jung-Tsun Lee, right? I hope pronounced correct. So he's currently postdoctoral fellow at the Center for Cosmology and Astroparticle Physics at Ohio State University. And before that, he got his PhD at the University of California, San Diego, working on dark sector physics with astrophysical and cosmological context and implications. Before that, he got his MA and Bachelor of Science at the National Tsinghua University of Taiwan. So he specializes in cosmic ray transport in the inner heliosphere, in solar atmosphere, and modeling of gamma ray emission. We have had the pleasure to work together for about a year on a very exciting problem, and you have the privilege here of having one of the few experts in the world on the topic. So the floor is yours.
Yeah, thanks for having me. Hi, I'm Jung-Tsung Lee. I'm a postdoc at Ohio State University. And today I'd like to talk about the gamma ray emission. Sorry, give me a sec.
Yeah.
Yeah, I'd like to talk about a continual GeV to TeV gamma ray emission from our sun. Okay. And before I talk about detail, I'd like to start with something simple. So why are we interested in the continual GeV to even TeV gamma ray emission from the sun? Why are they interesting? And the reason is that the sun itself does not emit GeV to TeV gamma rays. We know that the photosphere temperature is about 6,000 Kelvin, so that corresponds to the visible light, so not quite gamma ray. If we move a little bit away from the photosphere, the corona temperature can reach few million Kelvin. That corresponds to EUV and X-ray, so that goes like up to several keV. And also we know there's a good theoretical understanding about the corona heating. They mostly come from the wave-driven turbulence and or reconnection. So corona could not emit the continual GeV to even TeV gamma rays. Now, occasionally there are big events from the sun, such as solar flare and the corona max ejection. They can produce a shock or shock-like environment that can accelerate the proton up to few GeVs, and therefore emits the gamma rays also up to few GeVs. However, those signals are typically very transient, meaning we can extract them out from the gamma ray observation from the sun. And yet, we still see the continual emission, gamma ray emission from our sun. And there are two channels that can cause the GeV to TeV gamma ray emission from the sun. The first is the inverse Compton scattering in the solar halo region. So solar halo means the region at around the sun. So it's not the sun, it's the region at around the sun. And the idea is that the galactic cosmic ray electron transported to our solar system, and they diffuse toward the sun, and they can interact with solar photon and boost the solar photon energy up to GeV to even TeV. And in the past, Fermi collaboration themselves have studied this before, and they have studied the gamma ray emission from the solar halo region from 100 MeV to 10 GeV, and the data point is the observation, and they have used a simple force field model to compare the theory with the data. And it seems like the theory works okay with the data in the solar halo region. And so therefore, in this talk, I will not be focusing on the gamma ray emission from the solar halo. The second channel is the hadronic scattering in the solar disk. So the solar disk means the sun itself. Okay. And the idea is that the galactic cosmic ray proton can reach the solar atmosphere. And here we are talking about very energetic gamma ray. So the primary proton is also relativistic. And therefore, when a shower happens, the daughter particle will be collinear with the primary proton. And so in order to see those gamma rays coming out from the sun, the incoming cosmic ray proton has to be reflected somehow. And on their way out, they interact with the solar gas, produce a neutral pion, and neutral pion decay to two gammas. And the figure on the right, this is the combined two observations. So first is the data taken by Fermi, the 12-year data. They have observed the gamma ray from 1 GeV all the way up to 200 GeV. And recently, HAWK, very high energy gamma ray telescope, has observed the gamma ray emission from the sun at around 1 TeV. And as a series, I'd like to understand what kind of a structure at the solar surface that causes the incoming proton to be reflected, and on their way out, they produce such a high energy gamma rays. So there are a few theoretical challenges about this topic. The first is, so we know that cosmic ray has to be reflected, obviously by the solar magnetic field. But the solar magnetic field spans a wide variety of scales. We know that there are a magnetic field in the interplanetary space, the open field region. As we get closer to the sun, we have an open field line and the network field. And if we go even toward the solar surface, we have all kinds of small scale structures. So the question is, what structure or what scale matters? Obviously, I could not consider all of them in one problem. So the question is, what scale matters and how do we deal with this problem? And the second is the spectral shape. So the Fermi observed very hard spectrum. The flux goes like energy to the -2, as shown on the right. And yet the HAWK observation shown that at 1 TeV, the spectrum is extremely soft. The flux scales as energy to the -3.6. And remember that the cosmic ray spectrum scales as energy to the -2.7. So it's neither -2, neither 3.6. And so what causes such a interesting spectral shape for the gamma ray emission from the sun? And the third theoretical challenge is the anti-correlation between the gamma ray flux observed and the solar cycle. So the figure on the left, the top is the Fermi observation during the solar minimum. And the bottom is the Fermi observation for entire solar cycle, 12-year data. And we can see that the flux is off by a factor 2. And it's also true for the HAWK observation at about 1 TeV. So you can see that that factor 2 spans from 1 GeV all the way to 1 TeV. So that's 3 decades of energy. And it's interesting that that factor 2 across such a wide range of energy. And that's something that we would like to understand eventually. Moreover, Fermi, because of the high good sensitivity, angular sensitivity from the Fermi telescope, we also observe the anisotropy of those high energy gamma ray emission from the sun. We find out that so the gamma ray fluxes from the polar region is relatively constant. However, the fluxes from the equatorial region is anti-correlated with the solar cycle. So during solar maximum, we see very little gamma ray emission from the equatorial region. That's interesting. That might have something to do with the corona hole distribution, or maybe some other reasons. That's something we are probing right now. So as a series, we like to analyze this problem in the most simple way to understand the nature of the problem. So the first question we like to ask is, at what height do those gamma ray emission produce? Okay, and we know that gamma ray emission comes from proton-proton collision to neutral pion, and neutral pion decay to 2 gamma. So the incoming proton has to accumulate enough column density in the solar gas to be absorbed and to produce a neutral pion. So we can estimate the column density of the incoming proton, and has to equate 1. And that tells us that those gamma rays are most likely produced at minus 1,000 kilometers to 1,000 kilometers from the photosphere surface. That's shown at about here. Below minus 1,000 kilometers, proton would be absorbed before they are reflected. So that's not interesting to us. Above about 1,000 kilometers, basically the gas density is too low to be absorbed. And so that won't produce a much of gamma ray emission that observed by Fermi and Hawk. So here we are really talking about the region, i.e. the chromosphere, the photosphere, and maybe a few hundred kilometers below the uppermost convection zone of the sun. So that's a very thin layer from the sun. And how do we deal with this problem? Sun's magnetic field is quite complicated. I thought that maybe the easiest thing that one can do is assuming that those galactic cosmic rays simply follow the interplanetary magnetic field and the open field lines reaching the sun. And as the particle approach the solar surface, it reach the structure called the network field, shown in the middle. At the bottom of the network field is the network element made by a lot of highly compressed magnetic flux tube. And they are distributed in the region between not granule. Granule is the cell of the convection at the photosphere surface. And in the region between in the region at the solar surface, there is also a lot of large convection cell. Each is about the size of Texas, about 1,500 kilometers. And between the large cells, there's a highly compressed magnetic region called intergranular magnetic sheets. And they are caused by magnetic flux explosion. And they can generate a magnetic field up to about 1,500 Gausses at the region between the granules. And they can form in the sheet-like structure, and also sometimes the tube-like structures. And the idea here in our work is that, okay, those particles, they come from the open field line, reach the network field, and eventually reach all those flux tubes near the solar surface. And so we like to inject the cosmic ray to those regions at the region near the solar surface. However, that idea sounds wonderful, but we know that it's going to break down when the particle energy is very high, because as the particle energy reaches some kind of scales, they have very large Raman radius, and they can easily escape the flux tube, and they have to go to somewhere. And as they escape the flux tube, some of them just strike the solar surface. However, some of them can strike the intergranular sheets and enter those highly intensity magnetic sheets. I call it the flux tube. Okay, so here our model schematic is that we inject the particle in the flux tube. High energy particle can exit the flux tube and enter the flux sheets. And those particles are reflected by the mechanism called the magnetic bottle effect. Idea is that particle comes in as they approach toward in the region of the sun, they becomes nearly horizontal, and the radial component of the magnetic field can kick the particle, and that causes the particle to start spiral out. So initially, particle spirals in, become horizontal. On the way out, they spiral out. Here, the key factor here is how the particles are kicked by the radial component and how that magnetic butterfly effect works. And so we have to solve the magnetic structure of the flux tube and the flux sheets. Here, we assume that the loss structure is undergoing the magnetostatic equilibrium with ambient gas. So we can use the Greg-Schaffner equation to solve the tube structure for the flux tube and the flux sheets. And here's the summary of our model assumption. We assume that particle injected at the height of about 1,600 kilometers, so that's chromosphere surface. And we had the particle going through the chromosphere, photosphere, and maybe the uppermost convection zone. And the intensity of the injection is the same as the data taken by the AMS2 and the CRIM, meaning now we did not consider the solar modulation of the cosmic ray from 1 AU all the way to the solar surface. And we also inject the particle isotropically, and that means we did not consider any possible anisotropy of the incoming cosmic ray protons. And lastly, I want to point out that in this talk, throughout this talk, turbulence, magnetic turbulence is not considered. Turbulence could potentially become an important pieces to this puzzle, and that is something that we are exploring right now. And this slide shows our simulation result for the chances that particle can escape the flux tube and enter the flux sheets. We find out that when the particle kinetic energy is below 100 GeV, they are mostly binded by magnetic flux tube, and either they just go toward the sun and die, or they got reflected on the way out, produce gamma ray. When the particle kinetic energy is above 1 TeV, they are not binded by the flux tube, and they would just punch through the flux tube. Some of them strike the surface and die. Some of them enter the flux sheets, and they might have a chance to undergo the butterfly effect, and on the way out, produce the gamma rays. And summing all those that we can sum in all the previous slides, we can calculate the gamma ray emission. So first is we need to understand how many gamma rays are produced in each interaction. And the second is the incoming cosmic intensity. Here we just take the data from 1 AU. And third is the chances that they are absorbed. Once the gamma is produced, they still stream through the solar gases. So there's still a chance that those gamma rays can be absorbed by the solar gases. And we consider all of them, and we can do the simulation, particle simulation in such a structure. And here's our results. So the data point is the Fermi and the Hawk. And the first line, the green line, is the fluxes that one can get from the flux tube. And you can see that the flux tube contribute mostly the energy below 100 GeV. And that is because when the proton kinetic energy is above 100 GeV, they are not going to be binded by the flux tube. And the purple line here, the bump here, is the gamma ray emission from the flux sheet structure. And you can see that they only contribute to the high energy region. That is because the low energy particle will never reach the flux sheets in the first place. And the combining of the two gives us the gamma ray, total gamma ray emission from our theory prediction. And so far, I only talk about proton. However, there are helium in the cosmic ray components. There are also helium in the solar gases. Heliums are important. Once that is factored in the problem, the total gamma ray fluxes can be enhanced by about factor 80. So this is called a nuclear enhancement factor. And so the thick black line is from our theory prediction. And as you can see, while the theory line doesn't exactly overlap with the data, it's close. It's off by about factor 2 to factor 3. But the key factor here is we try to understand what kind of structure are important to this problem. And we also find out that from our simulation, we find out that the gamma ray emission mostly likely occur from 0 kilometer, i.e. the photosphere surface, to 400 kilometers above the photosphere surface. So this is just the photosphere layer. So it's very thin there at the surface of the sun. And here's my conclusion. So here we consider one tube and one sheet as the most simple model that one can do. And we find out that the hot spectrum observed by Fermi gamma ray telescope is caused by the combination of the tube and the sheet. And the very steep spectrum observed by Hawk is most likely due to a finite sheet structure, and therefore particles are unlikely to be captured by the sheets. And in the future, we have to explore the anti-correlation between the gamma ray flux in the solar cycle. And also, as I pointed out earlier, turbulence should be important. There are two components. One is open wave-driven turbulence. The other is the convection-driven fluctuations. Both could be important. We don't know the answer yet. That's something we are exploring right now. Thank you. That's all my talk.
Thank you so much. Do we have any questions from the people here? No, maybe I can ask one. Oh.
We might expect that the main effect of magnetic turbulence would be pitch angle scattering. Would that tend to decrease the likelihood of reflection?
That would increase the total gamma ray emission from the sun. And that is because as a particle pitch angle scatter and when they walk through the solar gases, they have a higher chances to accumulate column density and therefore produce more gamma ray emission. So we expect that any kind of fluctuation or turbulence should be able to produce more gamma rays. Yes.
Other questions? No. Oh, another.
Great, thank you. I know you said it's maybe a future step, but do you have any sense of why you have the anti-correlation with the solar cycle?
No. So we know that the anti-correlation causes something to do with magnetic field, but it's unclear to us whether that is caused by something at the photosphere surface, or maybe it affects the large-scale magnetic field and inhibit the particle to reach the photosphere in the first place. So it's totally unclear to me at this point, but it has to have something to do with magnetic field. Yeah.
Okay. Other questions online? I was just wondering, so you said you consider the flux transmission of the photons once they're produced through the photosphere and chromosphere. So what is the energy dependence of this transmission effect? Is more important low energies?
Oh,
lower energy?
The reabsorption?
Yeah,
the
gamma ray. Yeah.
Oh, it's going to be energy independence for gamma ray energy above 1 GeV.
Okay.
So that's something one can find in the particle data group. Yeah.
All the way to the TeV thanks.
All the way to TeV, yes. But below 100 MeV, it's highly dependent on the gamma ray energy.
Okay.
Yes.
All right. Okay. Thank you. Any other question? No? Okay. So let's thank Ruth again. And see you next week.